bridge segments. In locations where the bridge spans the water, shoring towers are erected around the piers to support the construction sequence. The construction process for the causeway involves several critical steps. It begins with the installation of board and cast-in-place concrete piles. These piles are created by drilling shafts into the ground to specified depths and diameters, as determined by the design. A steel reinforcement cage is then lowered into each shaft, which is subsequently filled with concrete. Groups of piles are connected by a pile cap, which serves as a rigid foundation for the bridge structure and helps distribute the load from the piers to the piles. Each pile cap supports one or more reinforced concrete piers, which act as the main supports for the bridge. The bridge superstructure rests on these piers. Before the precast segments are mounted, bearings are installed on top of the piers. These bearings are crucial for accommodating movements and ensuring the stability of the bridge. The bearings in bridge construction allow segments to accommodate expansion and contraction under high pressure and withstand rotational and translational movements as per design requirements. These bearings are custom made to fit the specific needs of each bridge. A segmental bridge is built using short sections or precast segments rather than large sections, which is the traditional method. These concrete segments are constructed in a precast yard and then transported and hoisted into place. In the short line casting method, each segment is cast in a stationary steel mold against the previously cast and hardened segments. After 10 hours, the freshly cast segment, known as the wet cast segment, is moved to the match cast position to ensure perfect alignment when assembled. The match cast segment is then transferred to the storage area the next day.
Put one bolt, he says. It'll be fine.
During erection, segments are lifted into position around a supporting pier, and the adjoining match cast faces are coated with epoxy. Temporary post-tensioning bars are installed and stressed to attach the segment to the cantilever. Once a balancing segment is in place on each end of the cantilever, post-tensioning tendons are installed and stressed from one end of the cantilever to its balancing mirror segment on the other side. As more segments are added, additional cantilever tendons are incorporated.
We can all get high if we want now. We can all get a piece of the pie.
Upon completing a cantilever with all segments symmetrically fitted, a link slab is cast at mid-span to connect subsequent cantilevers, forming a complete span. Finished cantilevers are connected at their closure joints. Using a launching girder for erecting viaducts offers several advantages, particularly in reducing traffic interface, which is crucial in crowded areas like the junctions at King Faisal Highway and Sheikh Hamad Highway. One significant advantage of this technique is the speed of bridge deck erection, given that segments are precast. This method reduces the on-site assembly time significantly. Moreover, it enhances safety by reducing the number of workers required on-site since most of the manpower is shifted to the precast yard. The short line casting method is highly advantageous in balanced cantilever bridge construction. It provides a precise system for gauging measurements and detecting errors in the proportions of individual segments. This method allows for on-site adjustments and corrections, ensuring the structure's longevity and offering a cost-effective solution with a faster construction pace. Traffic management for the project is divided into 9 stages, beginning with stage TM1 and concluding with the end line. Initially, new roads were built outside the existing Al Fateh Highway. Traffic was then diverted to these new roads, allowing the existing Al Fateh Road to be closed for the construction of piers, piles, and the main bridge structure. This process was coordinated with a design consultant to ensure efficiency and safety. Six Construct, the contractor, implements an internationally approved safety, health, environmental, and quality management system. This system is overseen by the design consultant, who ensures quality control at all construction phases. Continuous on-site testing of fresh concrete and soil compaction, along with material property testing at specialized third-party laboratories, is integral to the process. Each construction material undergoes testing according to predetermined plans and standards to verify its properties as specified in the design. Maintaining traceability is crucial for quality control and compliance with specifications.
Yeah, I know, over there.
In terms of quality, the project team collaborates closely with the contractor, reporting progress to the client. This prestigious project, currently the largest in Manama, adheres to high-quality standards. Testing of bearing components, vital for maintaining the bridge's balance and durability, is conducted in Italy and subjected to additional tests by other quality control institutions. Bridge installations require meticulous planning and the use of heavy-duty machinery to ensure the safe and efficient placement of structural components. In Israel, a recent project involved the installation of concrete beams, showcasing the use of powerful hydraulic cranes. In one phase of the project, 200-ton concrete beams were installed using two hydraulic cranes with capacities of 500 tons and 400 tons, respectively. These cranes were selected for their immense lifting power and stability, which are crucial for handling such heavy loads. The 500-ton crane, with its superior lifting capacity, was positioned to bear the majority of the load, ensuring that the beam could be lifted smoothly and safely into place. The 400-ton crane provided additional support, maintaining the beam's balance and alignment during the lifting process. This tandem operation required precise coordination between the crane operators and ground crew to synchronize their movements and ensure the beam was installed without incident.
Right now?
Involved installing 80-ton concrete beams using two 250-ton hydraulic cranes. Despite the lighter weight of these beams compared to the 200-ton beams, the operation still demanded careful execution. Each of the 250-ton cranes was responsible for lifting one end of the beam. The dual crane approach allowed for greater control over the beam's positioning and minimized the risk of structural stress or damage. This method also facilitated the precise placement of the beams, which is essential for maintaining the integrity and alignment of the bridge structure. Both phases of the installation emphasize the importance of using cranes with appropriate lifting capacities relative to the weights of the beams. The crane's hydraulic systems provided the necessary power and precision, while their robust construction ensured stability under heavy loads. These operations also highlighted the critical role of experienced crane operators and support teams in executing complex lifts safely and efficiently. The manufacturing process process of pre-stressed concrete trusses involves a sophisticated series of steps and specialized equipment to create large, durable structural components capable of withstanding significant loads. This process combines engineering precision with heavy-duty machinery to ensure the quality and integrity of each truss. Design and planning. The process begins with meticulous design and planning. Engineers calculate the structural requirements based on the intended use of the trusses, such as for bridges, industrial buildings, or other large structures. This involves determining dimensions, load capacities, and the layout of reinforcing steel and pre-stressing strands. Material preparation. Reinforcing steel. Each truss requires substantial amounts of reinforcing steel, typically up to 5.9 tons per unit. This steel is cut and shaped according to the design specifications. Pre-stressing strands. Pre-stressing strands, critical for reinforcing the concrete against tension forces, are prepared next. Each truss may use around 40 pre-stressing strands, totaling approximately 1,650 meters in length and capable of applying up to 343 tons of pre-stressing force. High-strength concrete. A specially formulated high-strength concrete mix is prepared. This mix is crucial for ensuring the durability and load-bearing capacity of the truss. Up to 27 cubic meters of concrete are used per truss, tailored to meet the specific strength and durability requirements of the project. Formwork and casting. Hydraulic truss formwork. The manufacturing process utilizes hydraulic truss formwork capable of handling components up to 45 meters in length, 2.30 meters in height, and weighing up to 80 tons per unit. This formwork ensures precise molding of the concrete into the desired truss shape. And pre-stressing. Once the formwork is prepared, the high-strength concrete is poured, embedding the reinforcing steel and pre-stressing strands according to the engineered design. During or immediately after pouring, the pre-stressing strands are tensioned to apply the necessary force to the concrete, enhancing its load-bearing capacity. Curing and quality control. Curing process. After casting, the trusses undergo a curing process to ensure proper hydration and strength development of the concrete. This typically involves temperature and moisture control to optimize the curing conditions. Quality control. Throughout the manufacturing process, rigorous quality control measures are implemented. This includes testing the concrete mix, inspecting the reinforcing steel and pre-stressing strands, and monitoring the formwork to ensure dimensional accuracy and structural integrity. Handling and transportation. Specialized handling. Due to their size and weight, up to 67.47 tons per unit, specialized handling equipment such as custom crane slings are used to lift and maneuver the trusses safely during production and transportation. Transportation. Completed trusses are transported using trailer vehicles with up to 9 axles, capable of carrying loads weighing up to 99 tons. These vehicles are powered by heavy-duty towing vehicles with up to 550 HP, ensuring safe and efficient transportation to the construction site. installation and integration. Upon arrival at the construction site, the trusses are lifted into position using cranes and secured according to the project's structural plans. Proper alignment and integration with other structural elements are critical to ensure overall stability and load distribution. Final inspection and certification. Before being put into service, the installed trusses undergo final inspection and certification to verify compliance with engineering specifications and safety standards. This includes load testing and verification of structural integrity to ensure they meet the required performance criteria. This beam launcher is capable of placing prefabricated beams up to 60 meters long and weighing as much as 130 tons in locations that are otherwise inaccessible for conventional cranes, such as ravines and gorges. Assembly and initial positioning. Once the beam launcher is fully assembled and positioned at the starting point, the primary beam is auto-launched to reach the first bridgehead. Positioning the main supports. With the main supports in place, the system is secured to receive the beams and initiate the launching maneuver. The prefabricated concrete beams are transported from their fabrication site to the bridge using a tractor trailer equipped with a dolly. Following the bridge construction procedure, the same truck in reverse can bring the beam to the rear end of the launcher to start the maneuver. Lifting and moving the beam. When the beam is positioned beneath the front winch of the launcher, a hook is attached to lift one end of the prefabricated beam. In a coordinated movement, the winch and the tractor trailer move forward until the other end of the beam reaches the rear winch's position. The rear winch then lifts the other end of the beam. Once the beam is hoisted, the truck is removed. With the beam suspended beneath the launcher's main beam, the winches advance longitudinally at approximately 5 meters per minute, launching the prefabricated beam into the span where it will be installed. To place the beam in its designated spot, the entire system, along with the suspended beam, moves transversely. The main supports of the system are mounted on a transverse rail located at the rear end on the already installed beams and at the front end on the bridgehead. Positioning. When the beam is correctly positioned, the winches lower it onto the bridgehead supports. Once all the beams of a span are installed, the system is launched to the next span using auxiliary supports. The system supports itself at 3 points as it auto-launches, moving along the previously installed beams, causing the main beam to advance longitudinally across the bridge. When the front end reaches the next bridgehead, it is directly supported and secured. Notably, the rear and auxiliary supports require leveled wooden shims. Repetition and system removal. This process is repeated until all beams are installed. The system then exits the bridge using the same auto-launching procedure and is disassembled for removal from the construction site. This advanced method allows Constructor to efficiently and safely place massive prefabricated beams in challenging locations, significantly contributing to the progress of modern infrastructure development. Karapiro Viaduct is a crucial component of the Cambridge section of the Waikato Expressway, an extensive infrastructure project designed to enhance connectivity in the Waikato region of New Zealand. This 16-kilometer section begins south of the existing Tamahuri interchange and stretches to approximately 2.5 kilometers south of Cambridge town, connecting seamlessly with the existing State Highway 1. The viaduct, along with 3 interchanges and 4 other bridges, exemplifies modern engineering and construction prowess. The Karapiro Gully Viaduct itself is a remarkable structure, stretching 200 meters in length with its deck positioned 40 meters above the gully floor. The term viaduct refers to a bridge comprising several spans used to traverse a valley, and this particular viaduct is supported by 3 sets of columns. These columns rest on substantial concrete pads and are anchored deep into the ground through piled foundations, with the deepest piles extending 55 meters below the surface. The process of driving these piles into the ground involved a large crane equipped with a massive hammer, emphasizing the scale and complexity of the construction effort. The superstructure of the viaduct, which forms the top part of the bridge, is constructed from large steel beams. These beams support the deck, which is made from precast concrete panels. Additional concrete was poured over these panels to form a robust base, upon which the actual road surface was laid. The entire construction process was challenging due to the steep banks of the Karapiro Gully and the meandering Karapiro stream, necessitating meticulous planning and execution. The construction team undertook several significant steps to ensure the project's success. They built a heavy-duty access road to the bottom of the gully, installed a temporary bridge to cross the stream, cut back slopes to create a safe working area, and stabilized the ground with rock to support the heavy machinery. Hammering all 64 piles into the ground and reinforcing them with steel and concrete took 77 days. The viaduct columns, with a diameter of 2.6 meters, are solid concrete, and the central pier columns reach a height of 35 meters. A 280-ton mobile crane was employed to lift the steel beams into place, occasionally assisted by a 150-ton crane for more challenging lifts. Workers were elevated to special platforms where they used 23,000 bolts to secure the steel beams. The completed viaduct will feature a 23-meter wide deck, accommodating 4 lanes of traffic. Post-construction, the gully will be replanted with indigenous vegetation and oak trees to support local wildlife, and rainwater captured from the bridge deck will be treated to minimize environmental impact. Mumbai-Ahmedabad High-Speed Rail (HSR) corridor project marks a significant step towards revolutionizing transportation in India, emphasizing safety, reliability, and sustainability while advancing the nation's technological landscape. This ambitious project spans 508 kilometers, traversing key regions in Maharashtra and Gujarat. The HSR project promises to drastically cut travel time between Mumbai and Ahmedabad, thereby stimulating economic growth, boosting tourism, and supporting infrastructure development. A key facet of the project is the utilization of the renowned Shinkansen technology from Japan. Superstructure construction involves casting and erecting girders, such as the full-span box girders used in the Mumbai-Ahmedabad high-speed rail project. Each 40-meter girder, weighing approximately 970 metric tons, is cast in a single piece using 390 cubic meters of concrete and 42 metric tons of steel. Advanced machinery like straddle carriers, bridge launching gantries, and girder transporters facilitate the erection process, ensuring precision and safety. These girders are lifted and placed onto bearings atop the piers, a process known as girder launching, completed in as little as 16 hours. Additionally, bridge construction over several major rivers has been completed, with ongoing work over the Narmada, Tapi, Mahi, and Sabarmati rivers. The use of full-span box girder launching technology facilitates rapid construction over existing railway tracks and roadways without disrupting traffic. Moreover, the project's first mountain tunnel in Valsad district and the first steel bridge in Surat district have been completed. The laying of the reinforced concrete track bed, utilizing the Japanese J-slab ballastless track system, has commenced in Surat, marking its first use in India. Noise barriers are being installed along the viaducts to ensure a quiet and scenic travel experience for passengers. The rolling stock depot in Surat is also under development, further highlighting the comprehensive nature of the project. The $2,500 USD Habitera affordable house, many years ago, represents a remarkable achievement in cost-effective and rapid construction. Situated in Mexico, this 47 square meter home was erected in a mere 14 hours, requiring neither specialized equipment nor skilled labor. Remarkably, no prefabricated parts were utilized in its assembly. The total cost, inclusive of electrical and plumbing installations, underscores its affordability and practicality. While costs may fluctuate based on geographical location, the Habitera blocks employed in this project typically come at a lower price point than traditional 8-inch blocks. For this particular structure, 2,568 blocks were utilized, each priced at a modest 50 cents. This groundbreaking approach utilizes interlocking concrete blocks that can be assembled quickly and efficiently, resulting in a cost-effective alternative to traditional construction methods. At the heart of the Habitera system is its unique block design, which is fully interlocking, mortarless, and self-aligning. This design not only simplifies the construction process, but also significantly accelerates it, with installations occurring at a rate 10 times faster than standard concrete masonry units, CMUs. The block's precise fit within a 40 centimeters by 40 centimeters grid eliminates the need for cutting, saving both time and money on the job site. One of the system's key advantages is its accessibility to unskilled laborers. With minimal instruction, even those without specialized training can contribute to the construction process, further reducing labor costs and addressing shortages of skilled workers in certain areas. Additionally, the block's lightweight nature makes them easier to handle, potentially reducing the risk of on-site injuries. Beyond its efficiency, the Habitera system offers several practical benefits. Its integrated rebar and concrete filling provides structural stability, while its modular design allows for flexibility in construction, including the incorporation of door and window jambs. Moreover, the block's interlocking characteristics enhance seismic resistance, ensuring greater safety and durability in regions prone to earthquakes. The system's advantages extend beyond the construction phase. Habitera blocks can easily be waterproofed and insulated, providing a natural thermal barrier and further enhancing the longevity and comfort of the structures built with them. Additionally, the system's reliance on minimal mortar reduces the risk of water penetration and associated issues such as inadequate bonding and mortar cracking. Foundation Formwork EasyClick, manufactured by Record Holzman, offers a seamless solution for the efficient laying and processing of foundation structures. This innovative formwork system simplifies the construction process while ensuring durability and reliability. The assembly of EasyClick is straightforward and swift. The formwork components are easily put together and placed in the excavated foundation trench, providing a sturdy framework for the subsequent stages of construction. The joints of the formwork are connected using tongue and groove or plug-in tongues, ensuring a tight seal. Additionally, assembly foam is utilized to fill the joints, enhancing the stability of the structure. One of the remarkable features of EasyClick is its versatility. It facilitates various construction tasks, including the formation of corners, accommodation of drainage pipes, and the concreting process. This adaptability streamlines the construction workflow, saving both time and effort. The floor slab formwork component of EasyClick further enhances its functionality. The floor elements, equipped with shiplap, are assembled to create a complete floor panel. Mounting foam is applied, and system legs with tongue and groove are installed, securely connecting the edge and base elements. An XPS heel profile provides additional structural support, ensuring the stability of the floor slab. XPS, or extruded polystyrene, used in EasyClick's construction, offers excellent thermal insulation properties and mechanical resilience. It is CFC, HCFC, and HFC free, making it environmentally friendly. With compressive stress ratings ranging from 300 kilopascals to 700 kilopascals, XPS provides reliable support for various construction requirements. The assembly process of EasyClick is divided into 3 simple steps, allowing for efficient installation. The system supports multi-layer laying, with a maximum of 3 layers up to a total height of 300 millimeters, making it suitable for a wide range of applications. Moreover, EasyClick is designed for fast installation, eliminating the need for complex installation plans. The system also offers sealing options compliant with high standards, ensuring the integrity of the structure. With EasyClick, the construction of load-bearing floor plates with sealing according to required standards is simplified. The system legs, floor elements, and sealing membranes work together seamlessly to create a durable and watertight foundation structure. floor slab insulation formwork thermosystem represents a sophisticated solution for insulating floor slabs while simplifying the intricate process of construction. In the video demonstration, every step is meticulously detailed to illustrate the seamless integration and efficiency of our system, starting from the initial preparation to the final sealing. The installation process commences with careful placement of the floor elements. Each element is positioned with precision on the prepared surface, taking into account factors such as alignment and joint offsetting to ensure a seamless fit. Multiple layers are handled with particular attention to detail, guaranteeing optimal coverage and structural integrity. Following the placement of floor elements, assembly foam is expertly applied to create a secure foundation for the system legs. These legs, essential for supporting the formwork, are then pressed into the foam and securely fastened with screws. This step not only establishes a stable framework, but also facilitates subsequent stages of the installation process. With the foundation set, the next phase involves the meticulous placement of foil and reinforcement. The foil is carefully laid over the assembly foam, serving as a barrier against moisture and providing additional insulation. Reinforcement is then strategically positioned, ensuring proper distribution and alignment to enhance the structural integrity of the floor slab. The concreting process begins with the application of steel fiber reinforced concrete, eliminating the need for traditional reinforcement methods such as steel mats. This advanced concrete mixture not only simplifies construction, but also enhances the strength and durability of the floor slab, meeting rigorous performance standards and regulatory requirements. Once the concrete has been poured and allowed to set, attention turns to sealing against rising damp. The heel profile, specifically designed for this purpose according to DIN 18195 standards, is carefully removed to prepare the surface for sealing. A waterproofing membrane is then applied to the concrete surface, providing a robust barrier against moisture ingress. Throughout the installation process, Adherence to general guidelines and best practices is emphasized to ensure optimal results. Factors such as maintaining a clean installation surface, protecting formwork against deformation, and utilizing high-quality materials contribute to the overall efficiency and effectiveness of the system. The ring beam formwork with MBA stirrup system represents an innovative solution for the efficient construction of ring beams and lintels. Approved by Deutsches Institut für Bautechnik, this system combines ease of installation with structural integrity, promising to revolutionize traditional construction practices. At the heart of the MBA system lies the reinforcement cage, ingeniously designed as an intelligent stirrup system. This cage eliminates the need for manual assembly, bending, or rolling of reinforcement bars, streamlining the construction process significantly. With the reinforcement cage positioner, pre-assembled cages can be effortlessly integrated into the formwork, ensuring precise alignment and optimal structural performance. The formwork itself is engineered for swift and straightforward installation. Utilizing MBA brackets and spacers, the formwork can be securely attached to masonry, facilitating quick setup. The inclusion of brackets for longitudinal bar positioning further enhances efficiency, simplifying the placement of reinforcement elements. A standout feature of the MBA system is its versatility. Whether constructing ring beams or lintels, the system adapts seamlessly to various masonry thicknesses and heights, catering to a wide range of construction requirements. Additionally, optional components such as elevation profiles and anchor channels offer enhanced stability and flexibility, ensuring reliable performance even in demanding conditions. One of the system's key advantages is its ability to streamline construction while maintaining compliance with regulatory standards. With DIBT approval, builders can trust in the system's structural integrity and adherence to industry regulations, providing peace of mind throughout the construction process. The assembly process of the MBA system begins with its universal compatibility. All components are delivered fully prepared for installation, allowing for prompt positioning of the selected formwork at the desired location. This streamlined approach minimizes setup time, enabling immediate use of the formwork. Once positioned, the prefabricated and perfectly adapted reinforcement console is inserted into the formwork. This eliminates the need for manual bending or shaping of reinforcement bars, ensuring efficient assembly and structural integrity. Following the insertion of the reinforcement console, the lower steel bars are securely connected to the MBA clips. This step ensures precise alignment and stability, laying the foundation for a robust structure. Subsequently, the upper bar steels are inserted into the recess of the stirrups. The upper plug caps are then inserted parallel to the lower ones into the console mats, completing the assembly process. With these steps accomplished, the MBA system is ready for use, compliant with general building regulations and holding approval from DIBT under Z15.6 322. The MBA system offers a range of products tailored to meet diverse construction requirements. The MBA ring beam formwork, equipped with clips, eliminates the need for cumbersome reinforcement cages, simplifying ring beam construction while ensuring structural integrity. Additionally, the MBA ring beam formwork with clips and reinforcement cage positioner provides precise positioning of the reinforcement cage, ensuring optimal concrete cover at specified heights. This system aids in positioning and maintaining concrete cover for classic reinforcement cages, with the reinforcement cage positioner included free of charge for many MBA and MBA thermo dimensions. Sealing edge formwork is a crucial component in construction, ensuring structural integrity and providing a smooth finish to the edges of ceilings. In this overview, we'll delve into the various types of sealing edge formwork available, focusing on those made of wood concrete, extruded polystyrene, XPS, and expanded polystyrene, EPS. The versatility of sealing edge formwork is evident in its ability to adapt to different masonry types. L-shaped formwork elements are seamlessly attached using assembly foam, which minimizes swelling during installation. To prevent deformation during concreting, supplementary accessories such as re-anchoring points are provided, enabling easy connection to lattice girders. Thermal slab edge formwork represents the latest innovation in sealing edge construction. Composed of extruded polystyrene, XPS, this formwork boasts excellent insulating properties. Its slotted fiber cement foot ensures adaptability and stability, while the waffled surface serves as an ideal plaster base. The tongue and groove system ensures precise installation, reducing joint visibility. Additionally, a wood concrete base alternative offers further customization options. For projects where side insulation is unnecessary, the slab edge formwork HB provides a viable alternative. With a base made of 10 mm wood concrete, it offers ample support and adhesive surface for quick and secure installation. The Neo series represents the cutting edge in sealing edge formwork technology. Utilizing graphite insulation EPS, it achieves superior thermal insulation compared to XPS. The Neo ZB variant features a brick panel, while the Neo ZR boasts a brick red coated surface, making them ideal for brick buildings. These elements, devoid of a foot, are installed with a joint offset to eliminate continuous joints. The advantages of these formwork solutions are manifold. Quick installation, effective bridging of unevenness, and straight edges are just a few benefits. Moreover, the absence of joint bonding and the inclusion of tongue and groove systems streamline the construction process. Minimal stripping or removal, coupled with no need for release agents or formwork oils, further enhance efficiency. Installation instructions are provided in detail, ensuring seamless integration into the construction process. Surface preparation recommendations emphasize cleanliness and moisture control, essential for optimal adhesion. Various fixing options are available, from adhesive foam to steel nails, catering to different masonry types and insulation thicknesses. Forget about on-site supports and complexities. The Record Ceiling Edge formwork solutions offer reliable anchoring options at competitive prices. By addressing concerns such as deformation during concreting and formwork distortion, they ensure maximum security and efficiency in construction projects. The Emedu Advanced Building System is a paradigm shift in construction methodologies, offering unparalleled efficiency and versatility across various construction phases. Let's explore its key features and advantages based on the provided aspects. Foundations and foundations anchoring. The system begins with robust foundations, tailored to the specific project requirements. Emedu's innovative approach minimizes foundation size while ensuring optimal load distribution. Anchoring the foundations securely is facilitated by strategically placed rebars, providing a solid base for the structure. Panels positioning and panels connection. Positioning the panels is streamlined and precise, thanks to the system's lightweight and modular design. Whether for walls, floors, or other structural elements, the panels fit seamlessly into place, reducing construction time and labor costs. The connection between panels is secure and efficient, ensuring structural integrity throughout the building. Placement of reinforcement meshes and slab placement. Reinforcement meshes are strategically placed within the panels to enhance strength and durability. The system accommodates the placement of reinforcement meshes with ease, ensuring uniformity and consistency in structural reinforcement. Slab placement is simplified, with panels providing sturdy support for concrete pours, resulting in smooth and level floor surfaces. Orthogonal walls and stair panels. Orthogonal walls are effortlessly integrated into the Emedu system, offering design flexibility and structural stability. Stair panels are pre-engineered for ease of installation, eliminating the need for complex on-site fabrication. Their robust construction ensures safety and longevity, making them an integral part of the building's infrastructure. Electrical and plumbing installation. The Emedu system streamlines electrical and plumbing installation with dedicated chases and conduits embedded within the panels. This allows for efficient routing of utilities without the need for intrusive alterations to the structure. The integration of electrical and plumbing systems is seamless, ensuring functionality and reliability. Shotcrete application and roofing. Shotcrete application is employed for reinforcing and finishing structural elements, providing a durable and weather-resistant surface. Amadou's roofing solutions offer versatility in design and application, accommodating various roof styles and configurations. Whether flat or sloped, the roofing system ensures optimal performance and longevity. Concrete casting and finishes. Concrete casting with the Amadou system is a streamlined process, with precise molds ensuring consistent results. Finishes are tailored to project specifications, ranging from smooth surfaces to textured finishes, enhancing aesthetic appeal and durability. The Sadr Bridge, located in the heart of Tehran, Iran, is a monumental infrastructure project with a total length of 6 kilometers. The bridge features both double amplitude lanes and single lanes, each with a width of 11 meters. It is a multi-span structure composed of pre-stressed concrete box girders with a constant section. The spans vary in length, including 44 meters, 41 meters, 47 meters, and 50 meters. The construction of the main bridge will proceed span by span using the segmental method, and it will be erected by launching gantries moving from Pier WS+5 to Pier M112. The construction process will utilize 4 launching gantries for deck erection. 2 gantries will start work from Pier WS+5 M1, while the other 2 will commence from Pier M111 and M112. These gantries will move from both ends toward the center of the bridge until all 111 spans of the deck are erected. One of the key components of this project is the use of external cables. The external cables used are of the OBM type, consisting of 19 15.24 millimeter bare strands. These strands have an elastic modulus, EP, of 195,000 megapascals and a standard strength, FBK, of 1,860 megapascals. The anchorage type for these cables is OVMT 15 to 19, and the deviator is a Brown Titan type. The external cables are sheathed with HDPE pipes filled with cement grouting, and these HDPE pipes are connected using HDPE couplers. In each span, 18 external cable bundles are designed, with 2 cables reserved and 16 installed and stressed during segment erection. A total of 3,552 external cables, weighing approximately 3,000 tons, are used for the Sadr Bridge. The preparation for external cable installation involves several steps. First, a temporary platform is set up for installing and stressing the external cables. Coils of bare strands are lifted onto the deck by the crane of the launching gantry. The coils are placed into a decoiler to prepare for strand pushing. The strand pusher is installed in the forwarding direction of the launching gantry, and a curved steel tube with its auxiliary support is set up. During the erection of a single span segments, HDPE pipes are welded simultaneously. Once all segments are assembled, the HDPE pipes are installed in the box girder. Each HDPE pipe is first welded with an HDPE liner, then passed through the bearing plate and connected to other HDPE pipes using an HDPE coupler. For strand installation, the curved steel tube is connected to the strand pusher, and the head of the strand is pulled from the coil and run through the duct. The strand pusher is positioned in front of the external cable to be installed, and the strand is pushed until it emerges from the other end. The strand is then cut to the appropriate length using a wheel cutter. The process of multi-strand stressing involves the use of multi-strand jacks. Anchor heads and jacks are installed to fit tightly with the shafts. The external cable is stressed synchronously from both ends following a specific tensioning procedure. 0 to 15% delta control, then 30% delta control, and finally 100% delta control. The anchor is set after holding the load for 2 minutes. After stressing, the temporary hanger rods of the segments are removed and the launching gantry is moved to the next span. The final step involves duct grouting. The excess strand is cut off, leaving only 30 millimeters protruding from the anchor head. A thin layer of grease is sprayed on the inner surface of the protection cap, which is then installed. The grouting holes of the anchor plates are cleaned, and the grouting machine hoses and other components are connected. A high-speed mixer and UV3 grouting pump are used for duct grouting, with a preference for grouting the upper duct first. The stressing bed is a vital component in the production of pre-stressed concrete elements, serving as the platform where concrete is cast and the strands are tensioned. Preparing the stressing bed involves ensuring that it is level and free from debris, installing anchorages at both ends to hold the strands, laying out the reinforcing strands according to the design specifications, and applying a release agent to facilitate the easy removal of the concrete element after curing. Once the stressing bed is prepared, the strands are placed. This involves threading the strands through the anchorages and along the length of the bed, cutting them to the required length to ensure they extend beyond the anchorages for tensioning, and anchoring them at one end using enclosed grips or couplers. These anchors hold the strands in place during the tensioning process, which is critical for maintaining the required tension until the concrete has gained sufficient strength. At the detensioning end, enclosed grips are used to securely hold the strands under tension, preventing them from slipping during the curing process. Conversely, at the stressing end, open grips are employed to facilitate the tensioning of the strands. This process involves attaching the open grips to the strands, connecting a hydraulic jack to the grips, and applying tension by activating the hydraulic jack, which pulls the strands to the desired tension. Coupling is another essential aspect of the process, involving the joining of 2 or more strands to ensure continuous tensioning throughout the length of the concrete element. This is especially important for longer elements where a single strand may not suffice. Couplers are used to securely connect the ends of the strands, ensuring uniform tension distribution. Pre-stressed concrete technology is a sophisticated method that enhances the performance of concrete structures by pre-tensioning or post-tensioning the embedded steel reinforcement. This approach significantly improves the concrete's ability to withstand tensile stresses, resulting in more durable and robust structural elements. The actual stressing of the strands is a meticulous process that involves incrementally tightening the hydraulic jacks to apply tension, closely monitoring the applied tension to ensure it meets design specifications, and locking the strands in place once the desired tension is achieved. Concrete has cured and gained the required strength, the formwork is carefully removed. The detensioning process follows, which involves gradually releasing the tension in the strands, using hydraulic jacks to decrease the tension carefully, and removing the enclosed and open grips to allow the strands to transfer their stress to the concrete element. If necessary, the protruding ends of the strands are then cut. Bridge displacement involves using advanced techniques like Paul strand jacks, pump units, and precise control mechanisms to carefully move bridge components. These methods ensure gradual and accurate displacement, crucial for tasks such as bridge widening or replacement without interrupting traffic flow. Paul strand jacks are renowned for their robustness and reliability in handling heavy loads, while sophisticated pump units facilitate controlled movement, minimizing structural stress. The construction of Turkey's Yavuz Sultan Selim Bridge, also known as the Third Bosphorus Bridge, stands as a monumental achievement in modern engineering. This bridge not only establishes a vital third connection between Europe and Asia across the Bosphorus Strait, but also showcases advanced stay cable technology. Spanning the North Marmara motorway, it alleviates traffic congestion in Istanbul by providing a strategic bypass. Innovative design and hybrid technology. The bridge features a traditional suspension bridge form with a shallow deck, chosen for its aesthetic harmony with the existing Bosphorus bridges. However, to achieve the necessary stiffness for the structure, a hybrid stay cable system was implemented. This rare combination of cable technologies enabled the support of the bridge's massive scale, with a record-setting main span of 1,408 meters and a deck width of 59 meters. The bridge's towers soar to 322 meters above the water, underscoring its monumental presence. Engineering challenges and solutions. Constructing such a large and complex bridge within a tight time frame of 36 months presented numerous challenges. The project required the development of new equipment capable of erecting, anchoring, and restraining the longest and heaviest parallel strand cables ever manufactured by Freycement. These cables, weighing 8,500 tons in total, were subjected to significant loads, necessitating innovative solutions to prevent sagging and reduce the risk of excitation. Specially designed deviators were introduced to control cable alignment at the anchorages. These components underwent rigorous testing to ensure they could effectively restrain the cables without damaging the protective sheathing. Achieving durability while maintaining the structural integrity of the bridge was paramount. Advanced stay cable technology. Wind-induced excitation posed a significant challenge, necessitating damping mechanisms for the free lengths of the cables. The design included 7.4-meter high masts with hydraulic pistons capable of a plus or minus 920 millimeter stroke, allowing the cables to move freely under service loads while mitigating excitation effects. On-site execution. The presence of the main cable overhead required adjustments to Freycement standard procedures for erecting and stressing the strands. The work had to be meticulously coordinated with other contractors to adhere to the completion schedule. Additionally, the post-tensioning, PT, work at a height of 305 meters and on the 1,372 meter backspan required precision and adaptability to handle the unique demands of the project. Demolishing the Alaskan Way Viaduct was a complex engineering feat. The 1.4-mile stretch of elevated highway ran adjacent to active buildings, bustling traffic, and pedestrian zones, necessitating a phased, precise approach. Using explosives was out of the question due to the proximity to populated areas, meaning crews had to rely on other methods to bring down the structure safely and efficiently. Phase 1. Initiating demolition. The first phase of demolition focused on the viaduct's double-deck sections. This initial stage required removing the roadway while leaving the support beams intact temporarily. Crews employed jackhammers to punch out the roadway, systematically breaking it into manageable pieces. Once the road surface was removed, concrete saws and cranes were used to cut and lift the support beams. North of Pike Place Market, the demolition involved single-deck sections. Here, machinery chewed through the structure with precision, taking extra care to protect the active train tracks below. This area required meticulous planning and execution to ensure that the trains could continue operating without disruption. Phase 2, Central Waterfront Transformation. The central waterfront area presented additional challenges and opportunities. As demolition progressed, crews worked to remove the road deck while ensuring the safety and integrity of nearby structures. Hydraulic crushing jaws were deployed to break down beams and columns efficiently. Dust control was a major concern. Water was sprayed to suppress dust, and curtains were used to contain debris. The water used in dust control was collected and treated to prevent contamination of the surrounding environment. Additionally, rubble from the demolition was strategically placed to protect underground utilities. This careful management allowed demolition to proceed without damaging critical infrastructure. As each span of the viaduct was demolished, cleanup operations followed closely behind. This sequential approach enabled streets to reopen incrementally, minimizing disruption to traffic and pedestrian flow. All steel and concrete materials from the viaduct were recycled, contributing to the sustainability of the project. Historical significance and the need for change. The Alaskan Way Viaduct was completed in 1953, offering a vital north-south route through Seattle. For decades, it facilitated commerce and mobility, playing an essential role in the city's infrastructure. However, the viaduct's design, typical of mid-20th century engineering, was not equipped to withstand modern seismic standards. Concerns about its vulnerability to earthquakes grew, especially after the 2001 Nisqually earthquake, which caused significant damage and highlighted the urgent need for a safer alternative. Phase 3, Southern Waterfront and Final Stages. The Southern Waterfront demolition posed its own set of challenges. In this phase, demolition took place mere inches from adjacent buildings, requiring even greater precision and care. Despite the close quarters, crews were able to safely dismantle the structure, ensuring that people and traffic continued to move without incident. The decision to replace the viaduct with a tunnel marked a turning point. The new State Route 99 tunnel, which opened in 2019, provided a more resilient and modern route for vehicles. This shift allowed Seattle to envision a waterfront free from the shadow of the aging viaduct, setting the stage for an ambitious transformation. The final stages of demolition included the removal of the old ferry walkway and the last remaining spans of the viaduct. This phase involved a systematic sequence of steps, removing the upper deck, the Columbia Street on-ramp, and the upper columns and crossbeams, followed by the footing removal near Marion Street. Each step was carefully coordinated to ensure safety and efficiency. For over 60 years, the Alaskan Way Viaduct was a defining feature of Seattle's waterfront, carrying people and goods through the heart of downtown. This double-deck concrete highway, while once a vital artery for the city, became seismically vulnerable and outdated as the years passed. The construction of a new deep-bore tunnel provided an opportunity to reroute traffic underground and reclaim the waterfront for public use. This ambitious project necessitated the meticulous demolition of the viaduct, transforming Seattle's iconic waterfront into a revitalized urban space.
We do that very well. When you have a bridge that was built 50 or 60 years ago, it's not like modern construction that you see now. When we first started
Communication and coordination. Effective communication and coordination were critical throughout the demolition process. Multiple teams and stakeholders had to work together seamlessly to keep the project on track and maintain safety protocols. This included regular updates, strategic planning meetings, and constant monitoring of progress and safety conditions.
These curves have to be up 100% of the time. We used the biggest machine we had to take down the upper girders. We had 1,600 ton of squeezing power.
The collaboration extended to the community as well. Keeping the public informed and addressing their concerns was a key aspect of the project's success. Clear communication helped mitigate the impact on residents and businesses, ensuring that everyone understood the benefits of the transformation and the steps involved in achieving it.
And then we'll remove the footage. There's so much material, you can't haul it all fast enough. So you gotta get it flattened out and leveled up where you can work on it.
The new waterfront.
Cleanup crew will come
With the
behind.
viaduct removed, Seattle's waterfront is being reimagined as a vibrant, accessible public space. The removal of the aging highway opened up new possibilities for urban development, environmental restoration, and public enjoyment. Plans for the new waterfront include parks, pedestrian pathways, bike lanes, and public gathering spaces, all designed to enhance the natural beauty and cultural significance of the area.
We're recycling all the bark, all the concrete's being recycled. We're putting the concrete back in the tunnel. This demolition business is
The transformation is not just about aesthetics, it also addresses environmental and social goals. The new waterfront design includes green infrastructure to manage stormwater, habitat restoration projects to support local wildlife, and public art installations that celebrate Seattle's cultural heritage.
Everybody's watching and spotting for each other. Even your water guys, they're communicating with the operators. Depending on which way you're wrecking and which way the sun's coming in, the water...
The careful dismantling of the Alaskan Way Viaduct marked the end of an era and the beginning of a new chapter for Seattle's waterfront. The project showcases the city's commitment to innovation, sustainability, and community engagement. As the new waterfront takes shape, it promises to be a dynamic and inclusive space that reflects the values and aspirations of Seattle's residents.
The public just watching us work. We hear a lot of good things from the public. You see some of the tenants that's up in these buildings, they're putting up big...
Bet Block System registered concrete blocks are crafted from premium C3037's concrete, ensuring exceptional quality and durability. Their innovative design, featuring unique protrusions, not only resembles popular blocks, but also streamlines installation, allowing subsequent layers to be laid without the need for binders or mortars. Concrete blocks offer a versatile solution for rapid construction and potential relocation due to their substantial weight and remarkable strength. This makes structures built with Bet Block System blocks highly resistant to pressure, ensuring longevity and stability. The application of Bet Block System extends to various building structures, including boxes, walls, partitions, material stores, composts, halls, and fences, among others. Its advantages are manifold: building various shapes of warehouses without foundations, laying blocks without binders, relocating blocks easily, adapting designs at any time, utilizing boards on unstable areas, pressing materials onto block walls, placing blocks without foundations, and offering a range of block sizes from 0.15T to 1.5T. Stone Strong 24 Strip, a revolutionary system of precast concrete blocks, is transforming the landscape of construction projects. These blocks offer unparalleled strength, durability, and versatility, making them an ideal choice for a wide range of applications. Gone are the days of traditional concrete beams prone to breaking and allowing materials to seep through the gaps. The Stone Strong system, with its massive 24-foot blocks, redefines what's possible in retaining wall construction. Unlike older methods like L-lines or T-type blocks, stone-strong blocks provide a robust solution that meets the demands of modern construction. The innovative hollow design of stone-strong blocks not only enhances their strength, but also makes them lighter and easier to handle. This design, coupled with interlocking features, significantly reduces installation time and labor costs. With the ability to install up to 12,200 square feet of blocks in a day, Stone Strong offers unmatched efficiency. One of the key advantages of Stone Strong blocks is their adaptability to various project sizes. Whether it's a small residential retaining wall or a large-scale commercial project, these blocks can accommodate any requirement. In fact, Stone Strong gravity walls can reach heights exceeding 20 feet, while MSC walls, with proper engineering and reinforcement, can safely approach 50 feet. Moreover, Stone Strong blocks come with a fully integrated drainage system, eliminating the need for additional parts or labor. This feature not only enhances the structural integrity of the wall, but also helps manage water runoff effectively, preventing erosion and ensuring long-term stability. In addition to their exceptional performance, Stone Strong blocks offer aesthetic appeal. Available in 4 custom patterns and capable of being stained to match any color scheme, these blocks seamlessly integrate into any design or landscape. Whether it's a roadside project, a commercial development, or a residential property, Stone Strong blocks enhance the visual appeal while delivering superior functionality. Furthermore, Stone Strong systems have undergone rigorous testing and evaluation to ensure compliance with industry standards and specifications. From structural integrity to geotechnical stability, these blocks have been thoroughly vetted by experts, providing peace of mind to contractors and developers alike. What sets Stone Strong apart is its commitment to innovation and excellence. By pushing the boundaries of what's possible in precast concrete technology, Stone Strong makes even the most challenging projects remarkably manageable. Its state-of-the-art engineering and design make it the go-to choice for contractors looking to deliver exceptional results. The manufacturing process of Belgian blue limestone, also known as petite granite, is a meticulous and time-honored procedure that begins with extraction. This natural stone, with its exceptional quality and mineral complexity, dates back more than 340 million years ago when the tropical sea that surrounded the region gradually receded, leaving behind fossil traces and creating the blue limestone of Hainaut. The extraction process takes place at Europe's largest ornamental limestone quarry, located in the Swanee region of Belgium. The first step is stripping, which involves removing the layers of clay and silt above the limestone, protecting it from the elements for millions of years. The valuable blue limestone deposit is typically found at a significant depth of approximately 70 meters below the surface. The benches are horizontal layers or steps that are cut into the quarry face. Each bench represents a distinct level within the quarry, allowing for organized and controlled extraction of the stone. Giant chainsaws are utilized to cut the limestone benches lengthwise. These specialized chainsaws are designed to withstand the demanding conditions of the quarry environment. They are equipped with diamond-tipped chains that effectively cut through the dense blue limestone with precision. Once the benches are cut lengthwise, crawler-mounted coal cutters are employed to perform transverse cuts. These robust machines are specifically designed for heavy-duty cutting operations in challenging terrains. The coal cutters feature powerful rotating drums fitted with cutting teeth that efficiently traverse the bench and extract the blue limestone blocks. The extracted blocks from the quarry face can be enormous, weighing approximately 100 tons each. To facilitate handling and further processing, these large blocks are split into smaller blocks using pneumatic drills and hydraulic spreaders. Pneumatic drills are used to create holes or channels in the block, while hydraulic spreaders are employed to exert controlled force and split the block along the predetermined lines. The use of pneumatic drills allows for precise positioning and drilling of holes, which ensures the controlled splitting of the blocks. Once the holes are drilled, hydraulic spreaders are inserted into the holes, and controlled hydraulic pressure is applied to create cracks in the stone. This process effectively splits the massive blocks into smaller, more manageable sizes for transportation and subsequent processing. The blocks are carefully labeled and conveyed to a raw materials processing area, where they undergo measurement, squaring off, and selection. The squared-off blocks are then sent to sawmills, where they are cut and processed into the desired sizes for further manufacturing. Processing area, the blocks of blue limestone extracted from the quarry are carefully labeled to ensure accurate traceability throughout the manufacturing process. The blocks are then conveyed to the sawmills, where they undergo further processing. At the sawmills, the blocks are cut into the desired sizes for manufacturing. Once the blue limestone blocks are squared off, they are transported to indoor or outdoor storage areas, which cover a vast space of 12 hectares. To ensure the evenness of the thick slabs, a technique called single belt cutting is employed. These machines saw off the blue limestone blocks at a speed of 180 centimeters, 5.9 feet per hour. Additionally, large circular blades are used to saw on-site blocks and slabs, ensuring the material is optimally enhanced. Throughout the manufacturing process, water plays a crucial role. Cali Arduino utilizes vast amounts of mine and spring water in its excavation operations. The water is responsibly managed and recycled. Water from the excavation processes is gradually purified through a series of settling tanks, allowing for its reuse. This responsible water management contributes to the company's sustainable and environmentally conscious practices. In the storage areas, the blue limestone slabs undergo various surface finishing treatments to enhance their aesthetic appeal. Advanced technology is employed to achieve these finishes. Slab polishers equipped with rotary heads are used to perform polishing, utilizing different types of abrasive segments, speed, and rotary pressure. This allows for a range of finishes, including light and dark blue honed, high polished, and no peso, and skirt, among others. In addition to the cutting center, a material recycling unit is present, where damaged or irregular tiles are cut into smaller units to optimize the value of the extracted material. Some tiles may also undergo specific finishes using supplementary machines, such as the trommel, which naturally patinates the tiles, giving them an aged appearance reminiscent of old church or farmhouse black stones. For certain artistic and sophisticated transformations, the expertise of stone cutters is indispensable. These skilled craftsmen work with curved pieces and decorative elements, utilizing their sensitivity, patience, and experience to create unique and intricate stone works. In granite mining, giant chainsaws are utilized to cut through the hard rock and facilitate the extraction process. Let's delve into the details of how these chainsaws work and the subsequent role of heavy excavators in separating the rock blocks. Giant chainsaws are mounted onto machines specifically designed for granite mining. These machines are equipped with an electrical panel and a hydraulic control panel to operate the chainsaw effectively. The chain itself has a total length of 26.37 meters, allowing for an extensive cutting reach. To enable the up and down movement of the blade, a single reducer is employed. This reducer facilitates the vertical motion of the chainsaw blade, allowing it to penetrate the granite effectively. Additionally, there is a travel reducer in place, known as the walking reducer, which enables the machine to move smoothly and position itself accurately for cutting. The chainsaw operator carefully positions the machine and initiates the cutting process. The powerful motor drives the chain along the guide bar, enabling it to slice through the hard granite. The operator skillfully guides the chainsaw along the predetermined cutting path, ensuring precise and controlled cutting. Once the initial cut is made by the chainsaw, the heavy excavator comes into play to further separate and remove the rock blocks. The excavator provides crucial support in the extraction process by utilizing its robust capabilities. To facilitate the separation process, small rocks are inserted into the initial cut made by the chainsaw. These rocks serve as wedges and are strategically placed to help widen the slot between the rock block and the surrounding surface. The presence of these wedges assists the excavator in effectively breaking apart the rock. The heavy excavator, equipped with a hydraulic arm and a bucket attachment, is positioned to work on the separated rock block. The skilled operator maneuvers the excavator, ensuring proper alignment with the rock block and optimizing the force exerted during the separation process. controlled pressure against the rock block. The inserted small rocks act as leverage, widening the gap and facilitating the separation. The hydraulic system of the excavator provides the necessary power and control to gradually push the rock apart. As the excavator exerts force, the rock block begins to separate along the cut made by the chainsaw. The controlled and precise actions of the excavator operator ensure a safe and efficient separation process. The Crema Marfil Coto Quarry, operated by Levantina in Penoso, Alicante, Spain, is renowned as the largest marble quarry in the world. To extract the marble from the quarry, Levantina utilizes a combination of modern machinery and heavy equipment. Chainsaw machines, diamond wire cutters, drills, excavators, bulldozers, and trucks play crucial roles in the marble mining process. These tools and machines enable efficient extraction and transportation of the marble blocks. One of the key machines used in marble mining is the chainsaw machine. This powerful tool incorporates a chainsaw fitted with diamond-tipped blades. The chainsaw machine allows precise cutting of the marble blocks in various directions, facilitating the extraction process. It is particularly useful in cutting through rough surfaces and extracting large blocks of marble. Diamond wire cutters are another important tool in marble mining. They consist of a long, flexible wire embedded with diamond beads. The wire is looped around the marble block, and as it moves, the diamond beads cut through the stone. Diamond wire cutters offer high precision and efficiency, allowing for the extraction of blocks with minimal waste and damage. Heavy equipment such as drills, excavators, bulldozers, and trucks are employed for various tasks in marble mining. Drills are used to create holes in the marble, allowing for the insertion of explosives for controlled blasting. Excavators are utilized to remove overburden and extract the marble blocks from the quarry. Bulldozers are employed for leveling the terrain and clearing debris, while trucks transport the extracted marble blocks from the quarry to the processing facilities. Marble is a versatile and highly sought-after natural stone that has been used for centuries in various applications. Its unique beauty, durability, and range of colors and patterns make it a popular choice for both functional and decorative purposes. The production of marble is a global industry that caters to diverse sectors and markets. One of the primary applications of marble is in the construction industry. It is widely used as a building material for flooring, walls, countertops, and decorative elements. The elegance and sophistication of marble enhance the aesthetic appeal of residential and commercial spaces. The versatility of marble allows for a wide range of finishes, from polished and glossy to honed or textured, catering to different design preferences. Marble is also extensively used in sculpting and artistry. Renowned sculptures throughout history, such as Michelangelo's David, have been crafted from marble. Its malleability and ability to withstand intricate carving make it a preferred choice for sculptors around the world. The unique veining and color variations in marble add depth and character to artistic creations. In addition to construction and art, marble finds applications in interior design, furniture manufacturing, and landscaping. It is commonly used for fireplace surrounds, tabletops, bathroom vanities, and decorative objects. The natural elegance and timeless appeal of marble lend a touch of luxury to interior spaces and furniture designs. The production of marble is a significant industry worldwide. Numerous countries are known for their marble deposits and extraction capabilities. Italy, Turkey, China, India, Spain, and Greece are among the top producers of marble. These countries have extensive quarries and processing facilities that meet the global demand for marble. The production process of marble involves several stages, starting with quarrying and extraction of marble blocks. The blocks are then transported to processing plants, where they are cut into slabs or tiles using diamond saws and other cutting tools. The slabs may undergo further treatment, such as polishing or honing, to achieve the desired finish. Once processed, the marble products are distributed and sold to various industries and markets worldwide. Granite manufacturing in China has experienced tremendous growth, making the country a major force in the global granite industry. China's success can be attributed to its vast resources, advanced machinery, and skilled craftsmanship. With over 50% of the world's granite reserves, China has become a leading producer, extracting and processing millions of cubic meters of granite annually. Chinese granite manufacturers have made substantial investments in cutting-edge machinery and technology. State-of-the-art equipment, including diamond wire saws, bridge saws, and CNC machines, are widely employed in the production process. These machines enable precise cutting, shaping, and sawing of granite blocks, resulting in high-quality finished products. China's granite manufacturing sector comprises more than 5,000 manufacturing facilities equipped with advanced machinery. The manufacturing process begins with the extraction of granite blocks from quarries. Using diamond wire saws and diamond-tipped saw blades, the blocks are cut into manageable sizes. China's granite quarries produce around 10 million cubic meters of granite blocks each year. These blocks are then transported to manufacturing facilities, where they are shaped and finished to meet customer specifications. Skilled craftsmen utilize CNC machines and water jets to create intricate designs and precise cuts. Chinese granite manufacturers prioritize quality control to ensure their products meet international standards. Stringent measures are implemented throughout the manufacturing process, from quarrying to finishing. As a result, China's granite industry has obtained certifications such as ISO 9001 and CE, guaranteeing the durability and reliability of their products. China's granite manufacturing industry is a significant exporter, supplying granite products worldwide. The country exports approximately 70% of its granite production, valued at over $3 billion annually. Chinese granite can be found in numerous global projects, including hotels, shopping malls, office buildings, and private residences. The competitive pricing of Chinese granite, combined with its wide range of varieties, has made it a preferred choice in the global market. The multi-wire Jupiter GS220 is an advanced open-frame multi-wire machine designed and manufactured by Pedrini for the production of granite and marble slabs. It utilizes a set of diamond wires to perform fast cutting of blocks, offering high production capacity and reliability. The machine is available in various versions, offering different wire configurations and diameters to cater to different production requirements. The options range from 24 to 72 wires, with diamond wire diameters of 7.3 millimeters, 6.3 millimeters, and 5.3 millimeters. This versatility ensures that the GS220 can handle a wide range of cutting projects. One of the key features of the GS220 is its flexibility in cutting slabs with different thicknesses. It can handle slabs ranging from 2 to 10 centimeters, allowing for customization based on specific project needs. This adaptability makes the machine suitable for various applications in the marble and granite industry. The machine is designed to be user-friendly, with an interface that facilitates easy management of the diamond tools and the machine itself. Operators can program and control cutting parameters with ease, ensuring precise and efficient operations. The vertical movement of the machine is facilitated by columns and an upper transversal beam. These elements provide stability and secure the machine to foundations. The machine features rear ribs for securing it to foundations, transmission shafts for synchronizing vertical movement, and sliders with sliding gibs for supporting operational elements. The machine incorporates an automatic system for wedging slabs, allowing the operation to be performed without interrupting the cutting cycle. The machine offers both automatic and semi-automatic modes for wedging, providing flexibility to operators based on their preferences and requirements. The machine's driving group is equipped with a large driving wheel for the diamond wires. The wheel, with a diameter of 2.3 meters, provides a long arc of contact, enabling the wires to run smoothly without breaking. The wheel is balanced electronically to eliminate vibrations and ensure cutting precision. Pedrini has patented a covering system for the driving wheel using modular bands made of anti-abrasion material. This system allows for quick and easy replacement of individual covering bands without disassembling the wheel. The modular bands have grooves that enable precise positioning of the wires based on the desired slab thickness. The diamond wire's hydraulic tensioner is a key component of the machine. It consists of an upper tensioning roller and individual tensioning wheels for each wire. The tensioning wheels are driven by hydraulic pistons to maintain constant tension on each wire during cutting. The system compensates for wire length differences and stretching, ensuring consistent performance. The tensioning wheels are supported by plates made of a special aluminum alloy, providing durability and corrosion resistance. Each tensioning wheel is mounted on a swinging plate with easy inspection and maintenance access. The tensioning system offers uniform tension distribution, low maintenance costs, and includes the HBS, hydraulic balance system, for each wire. The E220NA polishing machine is a highly advanced and efficient solution for polishing marble slabs. The rotor spindle is a one-piece vertical sliding assembly with electronically controlled positioning through a transducer. This design allows for smooth and accurate movement during operation. The spindle is equipped with double motorization, eliminating radial stress on the bearings and enabling the center of gravity to align with the axis of rotation. This design ensures perfect individual centering, facilitated by references on the beam and a robust fixing system. The rotor spindle incorporates a pneumatic counterpressure system, which is supplied as a standard feature and can be adjusted from the auxiliary panel. A pressure gauge indicates the back pressure against the weight of the head, allowing operators to fine-tune the action of the head for maximum efficiency with both hard and fragile materials. B220MA uses a 520mm diameter polishing plate that accommodates 8 abrasives. The plate is constructed from a single piece of reliable and sturdy aluminium, with guides for the abrasives joints directly shaped onto the plate, eliminating the need for screws. The connection between the rotor spindle and the polishing plate is achieved through a multi-directional joint. This high-tech composite structure ensures unlimited endurance without the need for maintenance. The joint optimizes the operation of the abrasives, even when polishing irregular slabs, and preserves the integrity of the abrasives during the polishing of slab edges. The spindle holding beam's transversal movement is facilitated by oil bath ground rollers and controlled by 2 gear motors. These motors drive tempered and ground helical tooth pinions, which engage with the racks. The motors are synchronized through a connecting shaft. Additionally, pneumatic locking systems are incorporated into the gear motors to halt the beam in case of power failure or machine emergency. Special devices are in place to constantly lubricate the contact areas between the pinions and racks with oil, ensuring smooth operation and longevity. The pneumatic plants responsible for the up and down movement of the spindles are positioned on the rear side of the beam in an easily inspectable position. The St. Louis-Arzviller Incline, located on the Marne-Rhine Canal in Alsace, France, stands as a testament to engineering ingenuity and a pivotal piece of industrial history in Europe. This remarkable feat of engineering was designed to overcome a significant elevation change in the canal, facilitating the navigation of boats between 2 different water levels without the need for multiple locks. Constructed between 1964 and 1969, the St. Louis-Arzviller Incline replaced a series of 17 locks that previously navigated the steep slope of the Vosges Mountains. This traditional lock system was not only time-consuming, but also labor-intensive, requiring significant effort and resources to operate. The innovation of the incline plane offered a revolutionary solution to these challenges. The incline plane functions essentially as a giant elevator for boats, capable of lifting or lowering vessels in a single motion. Boats enter a water-filled caisson, or a giant bathtub-like structure, which is then either raised or lowered along a steep rail-guided slope. This method dramatically reduces the time needed for boats to traverse the elevation change compared to the conventional lock system. It also minimizes water consumption, as the incline plane uses a closed-circuit hydraulic system to move boats efficiently. From a technical standpoint, the St. Louis-Arzviller Incline is an impressive example of hydraulic engineering. The incline itself spans a length of 41 meters and can lift boats up to 900 tons. The entire operation is controlled by a sophisticated system of hydraulic rams and counterweights, ensuring smooth and precise movements. Beyond its technical prowess, the incline plane holds significant historical and cultural importance. It symbolizes France's commitment to modernizing its inland waterway infrastructure during the mid-20th century, enabling more efficient transportation of goods and materials across the country. This development played a crucial role in revitalizing the Marne-Rhine Canal as a key artery for commercial navigation in the region. Moreover, the St. Louis-Arzwiller Incline has become a tourist attraction in its own right. Visitors from around the world come to marvel at its engineering brilliance and to experience firsthand the unique sensation of traveling aboard boats lifted or lowered by the incline plane. The site also features an interpretive center that educates visitors about the history of the canal and the technology behind the incline. In addition to its practical and touristic significance, the incline plane is a point of pride